Hello, my name is Evan Jones Sawyer, and we are Team Mechanical Minds. And today, we're going to present on the Colorado School of Mines steam plant during the 2019 Cyclobot. So, first things first, imagine yourself in December in mines, and your teeth start chattering, you're shivering, you have goose flesh all over you. You realize you are cold and you're studying thermodynamics at the same time. And you really can't get anything done while you're so cold. And what the proud people of mines have done is to use steam to power the heating system around campus to make sure that we're not cold all the time while we're going for finals, definitely during this December time, while you're walking around campus, while you're making sure not to get hypothermia. There are tunnels all around that make sure the steam is pumped all the way through. However, you're going to need a high efficiency for the steam plant because you want to do it consistently. If you got like 50% half cold, half hot, it's like, it's not great. It's not great. You can't do that. So, in short, our objective is to investigate the steam plant and make sure suggest any improvements to the efficiency. I'm gonna pass it off to you.
All right, hi, I'm Adriana Elms, and for the way that we are able to analyze the plant, we have to first look at the whole system with each different components. More specifically, we analyze the combustion chamber, the heat exchanger, and the economizer. And to do so, we used the equations we had from thermodynamics, balancing the chemical formulas, and then found the efficiencies of each, and then find out where we could have increased the efficiencies.
Hi, I'm Hunter. So for our assumptions, we assumed constant pressure and temperatures in the surroundings, we assumed constant mass inflow and outflow through the economizer and boiler, that everything was one continuous system. We also assumed ideal gas and that all sensor readings for composition of air were dry mass and by volume. Here we go. So for the flame temperature, we started with pure methane gas, which was another assumption I forgot to mention, and then taking that in mind, use the sensor output readings in the flue data to match, combined with the stoichiometric equation to balance out what our inert gases were to set the model to account for that. After which, used ease to set the enthalpies for everything at the start state going into the combustion chamber and the flue, set those enthalpies equal to each other, and then had it output a temperature for us.
All right, so then with the efficiencies, we looked at both the efficiency of the heat exchanger in the steam plant and also the economizer. So to find the second law efficiency of the heat exchanger, we do the desired exergy out, and then we compare it to the exergy flow in. And then to actually do this, we looked at the different flow rates, and we used the mass flow rates and then also the exergy going through the system. So going into the heat exchanger, we had that exhaust gas, and then we had the exhaust gas coming out as well. So similar process for the economizer, that exergy flow out and then the exergy flow in. We had different states for the economizer because we are getting that flow out from the heat exchanger going into the economizer. So that's how we found the efficiencies.
Okay, so for the flame temperature, I ran the model for the given data points at the various times we were given, and found the output flame temperatures, which was between 2,800 and 3,200 degrees Fahrenheit. I also ran the simulation with two different scenarios. One if I reduce the relative humidity by 10%, and one if I reduce the excess air by 10%. And those have had different effects on the amount of on temperature of the flame. Found that reducing the relative humidity of the intake air didn't do a whole lot. We had on the order of 10 to 20 degrees Fahrenheit flame temperature difference. However, changing the excess air on the input accounted for more of a 160 to 213 degree Fahrenheit change. Now, while I was running the model, I was curious balancing whether my theoretical calculations would meet the data, and I found that I had around a 0.5 to 0.75% deficit in carbon at the end, as in the data for the CO2 and tiny amounts of carbon monoxide did not add up to the total amount of carbon inputted via the ambient carbon dioxide in the air and the fuel. So now that can either mean that the model was wrong, the sensors are not calibrated right, or we might potentially have a very minor fuel leak. It's most likely a model issue, but without further data, I cannot determine that at this time. And now, moving on to the graphs though, I graphed the different situations. Blue representing the model of what the flame temperature was with the data given. Orange representing if I reduce the ambient humidity by 10%, and then green representing if I reduce the excess air by 10%. There was a flame out recorded at one point, which is why we dropped down to 0 here. But since excess air had the largest overall effect on changing the flame temperature, I decided to graph that separately and found a very strong linear relationship with excess air and flame temperature, an R-squared value of 0.94. And from that found that about increasing excess air by 1% decreased the flame temperature by about 17 degrees Fahrenheit.
All right, so then for the results for the heat exchanger and economizer, we can see that we have optimized efficiency around 2,990 degrees Fahrenheit to about 3,000 up to even 3,015 degrees Fahrenheit. And so at these values, we had a heat exchanger efficiency around 98, and then we had the economizer efficiency around 80. So with the actual results that we got from the data from the real steam plant, we had the efficiency of the heat exchanger to be 92 degrees, and then the efficiency of the economizer to be 78%. So at lower flame temperatures, we have a more efficient heat exchanger and also economizer. So maintaining both of those at the consistent flame temperature in that range right here, we get 72% efficiency for both of those systems combined, which is a wonderful efficiency for a steam plant. And then we also found that to maintain that flame temperature, we need 28% excess air. And then our references Thank you so much for joining us, Mechanical Minds,
Thank you.
and thank you for your time.